the fluids has non-viscous. It's non-viscous. And 3, the fluids also is non-compressible. It's non-compressible. So i.e. can say does not change. We change in pressure. Change in pressure produce insignificant change in its density. So there are 3 assumptions. One, deriving the equations of continuity of the fluid flow. So we assume that the liquid is flowing steadily. That is a streamlined flow, and viscous, has no internal. This one say no internal resistance. Non-compressible, we made a change in pressure produce insignificant change in its density. So there are some very useful terms. So under that we look at the useful terms. So some useful terms. Number 1 is the volume flux. 2, we have what we call the mass flux. The mass flux. Another name for this one is the flow rate. So we've got those 2 terms which are very useful as far as fluid flow is concerned. So let's define the first one. Let's define the volume flux, and this one is defined as the volume of fluids. So this one is defined as the volume of fluids passing through a given sections of a tube by unit time. So that is that. So the definition is as per that. It's defined as the volume of the fluids passing through a given sections of a tube per unit time. The SI unit is meters cube per second. So that is the SI unit. Number two is the mass flux. The mass flux is also defined as so this one is defined as the mass of the fluids. So this one is defined as the mass of the fluids, that flows through a given specific section by unit time. So those are very good definitions, or good, or we say useful terms. We've got only two terms, which is volume flux and the mass flux. The SI unit of this one, SI unit is kilogram per second. Like that. So thereafter, then we are supposed to come up with the equations, some of the equations. So we can draw a tube. And then let's represent this dot as the fluids. And then we have regions or sections W. So that is section W. So the speed, the velocity of that flowing fluid, we give it VW, and then the area of this section, we call it LW. Now you can also consider another section along that tube. The velocity of that moving fluids, we can take it to be Vx, and then the area of this section, we can take it to be Ax. So this is our section X. Section X. That one is section X. So let's explain what is Vx, Vr, Vx, and Vx is the velocity of flowing fluids. At section X, and then Ax, Ax is the area of the cross section, area of section X, and then Vw is the velocity of fluids in sections W. AW is the area of section theta value, that. Now we have Ex, which is the velocity of the flowing fluids at section X. Same case to area. This is the area of that section along the tube. Theta value is the velocity of fluids flowing in this in that section. Eta value is the area of that section. Now, how do we determine now the volume flask? How do we determine the volume flask? Now, volume flask is equal to the area of the cross section. So volume flask is equal to the area of the section multiplied by the distance from our volume. Usually volume, when we are talking about volume, then we are looking at the area of the cross section. Usually the area of the cross section either multiplied by the height. So we are applying the same knowledge. So we are saying the area of the cross section multiplied by the distance. So our volume flask is going to be, we can consider this region, this section. So the area of the cross section is AX, and then let's also say the distance between this region and this region is X. So the distance between that, same case to this, from here back up to there, we call it, the distance is the value. So volume flux is equal to the area of the cross sections at X multiplied by the distance, which we are calling it dx. It's going to be our dx. So this one is going to be our dx, and this one dx. So that is that. And then what we're also supposed to do is that we say velocity Vx around that region is usually displacement. You divide by the time, which is the displacement is going to be our dx all over t. So we have that. So our volume flux is area of the cross section at that region X multiplied by that distance is going to give us that. And then the same case, velocity is usually given by the displacement, you divide by the time. Now I can erase this. Then, based on this knowledge, we can say Vx, which is the velocity, is equal to the dx. This only can be true if the time is equal to 1 second. Because we say Vx is equal to dx, we divide by t. So if t is equal to 1 second, 1 second, then the velocity is going to be equal to the dx. So now we can summarize by saying volume flux, therefore volume flux is going to be equals to ax multiplied by the Vx. So volume flux is going to be equal to the area of the cross section, area at section x multiplied by velocity at section x. Same case also to the other one, and also volume flux to the other one is going to be equals to the other one. Volume flux is also going to be equal to area and that multiplied by the theta value. And then another equation. So we have to note that the volume flux is equal to the area of the cross section at x multiplied by that. So in summary, in short, when you are looking for the volume flux and you are looking for the volume flux, then it is usually the area of the cross section multiplied by the velocity. A is the area, phi is the velocity. So for the flux, E is a phi, the area of the cross section multiplied by the velocity. Now let's look at another dam mass flux. From what we know, usually when we are given the density, it is usually mass over the volume. It is equals to that. So therefore, if we are looking for the mass, then it is usually the density multiplied by the volume. Now, so when you are looking for the mass flux, it is going to be the density multiplied by the volume flux is equal to the volume flux. We know volume flux from our earlier derivation. It was equal to A x phi x. This was the area of the cross section at x, and then that was the velocity of the fluid moving at that section x. So therefore, volume flux, the mass flux is going to be the density multiplied by the area multiplied by the phi x. And that one gives us the mass flux. So mass flux is given by the density, the product of all these terms: density, the area of the cross section, and then the velocity. SI unit, as we had earlier said, is given by mass, kilogram per second. Kilogram per second. So those are very good terms. So those are very good terms. So whenever you are asked to talk about the volume flux, that is the formula. And we say the mass flux is the mass of fluids flowing through a given sections of a tube per unit time. And the volume flux is also defined as the volume of the fluids passing through a given section of a tube by unit time. The formula of that is, when you want to get that, it is equal to the area of the cross section multiplied by the velocity.